Hello class. Today we're going to be talking about phase changes. In particular, we're going to be exploring what happens at a molecular level when we go from, say, a solid to a liquid and a liquid to a solid. So before we do that, a couple quick reminders. Whenever we break bonds, this always requires energy to do. Always. Whenever we make bonds, this releases energy. And understanding that is essential to understanding what's happening on heating and cooling curves, which is how we're going to often represent these phase changes. So I say here bonds or interactions. When I use the word breaking bonds or making bonds, really, when I'm talking about phase changes, I'm talking about interactions, those IMFs, those intermolecular forces that are holding them together in a solid. When we break those interactions, that's going to take energy. And if we're going, say, from a liquid to a solid and making new interactions, well, that is going to make energy. Now, what do we call those processes? If we have a reaction that requires energy, right, that is eventually going to take energy from your system, that is an endothermic reaction. So more energy in this case is used in the breaking of bonds than is generated by making new bonds. So if I did a little reaction in a beaker here and the beaker got super cold, that would be an endothermic reaction. On the flip side, we have exothermic reactions, where less energy is being used in the breaking of bonds than is generated by making new bonds. So in this case, we are generating energy. If I had that same reaction going on in a beaker and the beaker got super hot, well, that would be an exothermic reaction. So here are two different representations. In this graph here, we can see this is the energy level of our reactants, and here are products. And we can see that the energy level of our reactants is lower than our products. So where did this extra energy come from? Well, that was absorbed from our environment, so this is an endothermic reaction. Here we have our energy level of our reactants is higher than our products, and we have this energy as a result released, right? The difference is going to be the energy released, and that is an exothermic reaction. So again, endothermic, you're going to be taking heat from your environment. It's going to feel cold, whereas your exothermic, it's generating heat, putting it into the environment. It's going to feel hot. Understanding this is essential to understanding the processes of freezing and melting. So first off, let's talk about then freezing point and melting point. Well, your freezing point and your melting point are the same point. They are equal to one another, right? Where does water freeze? Well, it freezes at 0 degrees Celsius. Where does water melt? Well, it melts at 0 degrees Celsius. What is the difference though? When we're using the word melting, we're talking about a situation in which energy is being added, right? We're heating up that ice. If we're talking about freezing, we're talking about the opposite, where energy is being removed from your system. So this is where things are going to get a little complex. What is melting? What is actually going on? So this is going to draw on what we learned in the kinetic molecular theory. So if the stuff I talk about in regards to kinetic energy isn't making sense, go back and review that. So what is melting? We all know it. It's where we go from solid phase to liquid phase. Now, let's say we had a block of ice. As we heat it up, the kinetic energy of those ice molecules, in this case water molecules, they're going to begin to vibrate faster and faster and faster and faster. Now, what is this going to do? This is going to cause our solid to expand, right? Those particles are going to be moving slightly further and further apart as we heat it up. Now, eventually, we're going to reach a point where those particles can break free of those interactions, of those IMFs that hold them together as a solid, right? Once they break free, they are now able to flow. They become a liquid. So, key point, remember, breaking bonds, breaking interactions, this takes energy, right? This takes energy. So, as we are adding energy to ice, let's say we start out with minus 20 degree ice, some very cold ice, and we heat it up. What's going to happen to the temperature of our ice? Well, it's going to go up, right? It's going to go up and up and up till we reach 0. And once we reach 0, it plateaus. The temperature of your ice will sit there, and it will not change until all of that ice is melted. So if I had, a glass of water with a ton of ice in it versus a glass of water that's been sitting out for a while and there's only like 1 cube of ice left, which one is going to be colder? Well, their temperatures will be exactly the same. They'll be exactly the same. Because when the melting point is reached, heat energy is no longer increasing the kinetic energy. The energy we are adding to the system isn't causing your particles to vibrate faster in this case. Where's that energy going? Well, it's going into breaking the interactions between those solid particles. So once your ice begins to melt at 0 degrees Celsius, it will stay there until all of the ice has melted, because all of the energy being added is going into breaking bonds. Students here always ask me, well, Mr. Soul, why don't we just add like a crud load of energy? Why don't we just, flame it? That'll make the ice temperature change. No, it'll still be 0 degrees Celsius. It'll just melt way, way faster. So keep in mind, just a refresher, if the energy, right, if it's not being utilized to increase kinetic energy, if it's being utilized to break bonds, that means that your temperature isn't changing at the freezing point because your kinetic energy isn't changing, right? Remember how I talked about a thermometer? What was the analogy I used? A thermometer is a speedometer for your molecules. So if your temperature isn't changing, the speed of your molecules isn't changing either. All of the energy here is going into breaking interactions, and therefore kinetic energy will not increase until all of the substance melts. So is melting then, is this an endothermic or is it an exothermic process? What is it? Think about that, right? Is it endothermic or exothermic? We are adding energy, and is the temperature, it was staying the same, right? So where's that energy going? Where's that energy going? Well, this process must be endothermic, right? We are breaking interactions between those solid particles, and therefore it is an endothermic process. All right, so now let's talk about freezing. Freezing, aka solidification. Obviously, we're going here from liquid phase to solid phase. Now, when we cool something down, we are decreasing the kinetic energy, right? We have these liquid particles that are flowing past each other. They're moving super quick. And as we decrease the temperature, they're now moving slower and slower until they reach a point where new interactions will form, right? Now they will become a solid. So, remember, breaking bonds takes energy, but forming bonds, forming new interactions, well, that is going to release energy as a result. So, the energy released from these new interactions, it needs to be removed, right? So believe it or not, when you freeze something, it is actually releasing energy to your external environment. And if you want to continue freezing it, you need to continually remove that heat being produced. So the removal of energy does not decrease the kinetic energy until all of the substance is frozen, right? Because what's happening? Well, we've been removing energy at a constant rate from, say, our water here, and it begins to freeze. And when those water molecules form new interactions, this generates energy, and therefore we need to remove that from the system before we can continue to freeze more. So our temperature at our freezing point will remain constant, right? As we're freezing it, it remains constant until all of that ice has frozen, and then the removal of energy can further decrease our temperature. So the temperature remains the same until completely frozen. So is freezing then endothermic, or is it exothermic? What do you think? What do you think? Is it endothermic or is it exothermic? Well, we form new interactions, and when we form new bonds, new interactions, that is going to produce energy, so it is in fact exothermic. Now, based on that, you should now be able to make an assertion about, say, going from liquid to gas, boiling, right? Because we said when we go from a solid to a liquid, we said that was what? When we melt something, we are breaking interactions, right? It requires energy, so that's endothermic. Now, if we're going from a liquid to a gas, again, we are increasing the kinetic energy of those particles until they are high enough where they can break free of those interactions that hold them together in the liquid phase. So we are breaking interactions yet again. So as we go from a liquid to a gas, this is all going to be endothermic. Right? If you are moving in this direction, this is endothermic. It is going to require energy to break those interactions. Now on the flip side, if we are condensing gas, we are forming new interactions between our gas particles, right? Now it's becoming a liquid. And if we're going from a liquid to a solid, we're forming new interactions again to become a solid. When you form new bonds, new interactions, this generates energy. This is exothermic as a result. So if you are going in this direction, solid, liquid, gas, that is endothermic. If you are going from gas to liquid to solid, that is exothermic. Okay? So let's talk now about the factors that will impact your melting point and your boiling point of a substance. Keep in mind, your melting point is equal to your freezing point, and your boiling point is equal to your condensing point. They are one and the same. So I'm referring to both here when I'm saying melting point and boiling point. Okay, so the first thing, intermolecular forces. The greater the forces between your molecules, the harder it is to break them apart, and thus more energy will be required in order to do so. Therefore, you must have a higher kinetic energy and therefore higher temperature. So the greater the IMF, the higher the melting point and the boiling point. The lower the IMF, the lower the melting point and the boiling point are. Another big one is molecular size. Molecular size. So London dispersion forces do increase with increasing size. More shells of electrons, more electron shielding, more London dispersion forces. Another impact of large size tends to be larger mass. And what is the formula for kinetic energy? Kinetic energy is 1/2 mv squared. If we increase the mass at the same kinetic energy, we will have a lower velocity. So by increasing mass, we decrease the speed at the same temperature, and therefore it will have a it will have a higher melting point and boiling point as a result. Right? We increase mass, therefore to reach the same kinetic energy required to break those particles apart, it's going to require more energy because they're just more heavy, they're more massive. And lastly, we have ionic versus covalent bonds. In general, due to the lattice structure and the strong electrostatic interactions between your ions, ionic substances have extremely high melting points and boiling points. Covalent compounds, on the other hand, tend to have much lower melting points and boiling points. Now, there is one exception to this, and that exception is network covalent solids. So we talked a little about this when I talked about the properties of solids. Some solids can form, some solid covalent compounds can form crystalline lattice structures, and that gives them very high melting points and boiling points, right? Think of diamond, for example. So let's now look at heating and cooling curves. So how do we represent phase changes? This is one way you're going to see it represented on your test at the end of this unit. So phase changes, just a reminder, they are physical changes. They do not involve a change in the composition, chemical composition of a substance. Instead, they involve a change in the forces of attraction among the particles of a substance. And the role energy plays during phase changes is very specific. We touched on those specific parts. Note, lots of students, when they see these flat parts of the graph I'm about to show you, they think that the Bunsen burner was turned off, right? But that's not the case. What's happening here is there is a constant amount of heat energy either being removed or added to the system. There is no change at all during this graph's time scale. Okay, so the amount of energy being added or taken away is constant. So here's an example of a heating curve, where our substance starts out very cold, aka it's going to be a solid at that point. We're going to heat it up till we hit the melting point, where it is then going to be in liquid and solid phases, right? It's transitioning to liquid phase, and then it's going to heat up all the way to the boiling point, and then again at the boiling point we're going to have that transition where there's liquid and gas present, and then eventually it's going to be all gas. Now, let's talk in a little more detail what's happening at those points. So at first, we have a very cold solid. So we're adding heat to the system, and now those particles are going to vibrate more and more and more, and they're increasing in their kinetic energy. Eventually, you'll reach a point where your temperature flatlines, where that addition of heat is no longer increasing kinetic energy, and it's here where that energy is being used to break apart the interactions that hold it together in a solid. That is part B. And the temperature, the kinetic energy, will not begin to increase until all of that solid has been broken down. Now in C, we have now melted our solid. It's all liquid, so adding energy will now again increase kinetic energy, and those particles will move faster and faster and faster and faster until again they reach a point where the kinetic energy doesn't increase anymore, right? Right here where it doesn't increase anymore, where that energy is now being used to break apart the interactions that hold it together as a liquid. Now that substance is turning into a gas, and once it's all turned into a gas, that gas now will begin to increase in temperature, aka increase in kinetic energy. So that's what's happening on a heating curve. Now a cooling curve will be the opposite of that. So again, if I were to put here, because again, we obviously just did water, right? If we looked, it was 0 degrees Celsius for the melting point and 100 degrees Celsius for the boiling point. So really we had ice up until we hit 0 degrees Celsius or 32 Fahrenheit, and then it began to melt there, right? It began to melt. And once all the ice was melted, we had water. The water heated up to the boiling point, and at the boiling point, it all turned into steam. And once it was all steam, it began to increase in temperature yet again. Cooling curves are the opposite, right? We start off with some very hot steam. As we remove energy from the system, we are cooling it down, and it will cool down until it hits that condensing point. And at the condensing point, the particles are now moving slow enough where they can start to form new interactions. And as a result of forming new interactions, that's going to release energy, and that released energy needs to be removed to continue the process of condensation. So that is why it flatlines there at 100 degrees. It will not continue to decrease in temperature until all of that gas has turned into a liquid. Now once all that gas is turned into a liquid, the temperature will drop until it hits 0 degrees Celsius, the freezing point, where again, those particles are now going to be moving slower until they can interact and form solids. And the new interactions formed in the making of a solid are going to again release energy. That energy needs to be removed, which is why the temperature again flatlines at 0 degrees Celsius. And once all of the liquid is frozen, the ice will begin to cool and cool and cool. So that was a lot to take in, but in essence, if you can understand what is happening at a molecular level in terms of freezing, in terms of melting, why the temperature plateaus at those points, you will do very well on the rest of the theory in this unit. Because next we are going to be talking about vapor pressure, boiling, and evaporation, which is going to build on the theory we talked about today. Okay, everyone, have a wonderful day.